everyone, and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over another calorimetry problem. So let's get into this. Excuse me. So in this problem we have a 12.5 gram block of iron at 195 degrees Celsius is dropped into 20.0 grams of ice water at 0.0 degrees Celsius. Now, the ice water, that means that there's ice mixed in with the liquid water, right? So the hot block is put into the ice water that has ice and liquid water together. The final temperature of the mixture is 2.0 degrees Celsius. So that indicates right away, if your temperature is above zero, then that means all of the ice had melted and any additional heat that was left after melting the ice increased the resulting leftover, the rest of the mixture up 2 degrees. So that's important to keep in mind. Assuming no heat was lost to the surroundings, how many grams of ice were originally in the ice water mixture? Okay, that's the question, that's the problem. They're giving us all this information here. They give us the specific heat of iron, specific heat of water, specific heat of ice. They give us the heat of fusion. Fusion is just the heat that's needed for melting. Fusion is just a fancy word for melting. So the heat needed to melt the ice and the heat of vaporization of water, that's the heat needed to vaporize or evaporate or boil away the water. Since the temperature only gets up to 2.0 degrees and water boils at 100, this is not going to be useful. We're not going to use that, so that's not going to come in. But the rest of it will be useful. Okay, so now that we've kind of looked over the information that we have, what's the strategy? For any type of calorimetry problem, the first thing you want to do is figure out what is absorbing and what is releasing heat in this exchange of heat during the process of the heat transfer, right? So we have a block of iron. The block of iron is at a higher temperature. So we know that the heat is going to always transfers from the hotter object to the colder objects. The block of iron is obviously the hotter object, so the iron is going to lose heat. So that's one Q value. So we need to mention our Q values here. So we have Q, Fe. So the Q of the iron, the heat that's released by the iron, that's one Q. What's another Q value? What's gonna absorb the heat? Well, if it's ice water, then you've got ice that's going to absorb the heat. So we're going to need the Q of the ice, right? The amount of heat absorbed by the ice. So this is the amount of heat released or given off by the iron. And then the ice absorbs some of that heat. And then notice that the ice is going to melt, become water. That's going to mix in with the rest of the water, and we're going to have water left over. So we're going to have the Q of water, W for water. Now, what's going to be very important and make this problem a lot easier is if we just mentally compartmentalize the water from the ice. Right? So what do I mean by that? If we just take this step by step, then it'll make it easier. So if we just focus on the ice melting before we deal with the water, right? Let's just assume for the sake of argument that all of the ice melts first before any water absorbs heat from the block. Now, that's not true. All of this absorption is going on at the same time. The block is heating up the water. It's heating up the ice at the same time. The ice is melting. As the ice is melting, the new water is absorbing more energy from the block. And so it's very complicated. But it works the same if we just compartmentalize. So if we just focus on the ice melting first, And then once all of the ice is melted, we can then focus on the liquid water absorbing the rest of the heat that's available to raise the temperature of the water. So I hope that helps. Okay, so right now, everything is at 0 degrees Celsius. The iron's at 195. We put the block of iron in, and everything starts to happen. So we've got our three Q values. The iron is giving off heat. The ice and the water is absorbing the heat. So that's a good beginning. So now, what do you do from here? So if you only have two objects between which heat is being transferred, then normally you would do the Q1 negative is equal to Q2, right? Because remember, the amount of heat being lost is equal in magnitude to the heat being absorbed. So they're equal, but they're opposite because one is losing heat, the other one is gaining that heat, right? What do you do when you have three or more? Well, you could set up the same thing. You just need to know which side is going to be the losing side, the giving away heat, and what's absorbing the heat, and make sure you have them on the right side. So if I was going to set this up, I know the iron block is giving off heat, so it'd be QFE minus, and the other two are absorbing the heat, so they would be on the other side, on the plus side. So it'd be Q of the ice plus Q of the water, and then I could just solve that and plug in the formulas for all of this. But I like to put it all on one side. So if I make this on one side, I just do plus QFE plus QFE. So then it becomes 0 is equal to Q of the ice plus Q of the water plus Q of the iron. So I don't have to worry about pluses and minuses and all that. But this is the same equation as this. It's just I rearranged it. So I like to use this one because everything is on one side, everything's positive, and the only thing you have to worry about is making sure that you put in the right numbers, you plug in everything correctly. Remember, the temperature change is final minus initial. If you get a negative temperature change, that's okay. It's supposed to be that way. As long as you do final temperature minus initial temperature, all of the pluses and minuses should work out. Okay? And this makes sense because all of the Q values, if we're assuming that all of the heat is transferred from one thing to the other, no energy is lost to the surroundings, then all of these added together should equal 0, right? Because remember, equal but opposite. So if I have a negative amount of heat being lost, and that's equal to a positive amount of heat being gained, if I add them together, then the result should be 0. Okay, so I'm going to use this equation here. So let me just leave that there. Now, what do I need to figure out the formulas. So let's rearrange this. Ice. So here, what's the formula for ice? Ice needs to melt, so we need the heat of fusion, which they gave us. So notice the heat of fusion of water or ice is 6.02 kilojoules per mole, right? So notice here that one, it's in kilojoules, and we have the rest of this in joules. So we probably don't want to put this in joules, right? And also, so let's go ahead and do that. So if I use my conversion factor, kilojoules is on the top. 1 kilojoule is equal to 1,000 joules. Kilojoules on top, so I'm going to put 1 kilojoule on the bottom, 1,000 joules on top. Kilojoules are going to cancel out. So now I'm just multiplying by 1,000. So this becomes 6 point, not 6 point. It's going to be 6, 0, 0, 6020, sorry. 6020 joules per mole. Okay, that's the first thing. The second thing is, notice that we have moles here. What are they asking for? How many grams of ice were originally in the mixture? But we got moles. So we can use this, we can convert moles into a number of grams. So the formula for this, and I'll show this a little bit later. So the formula is, I have to, in order to get the joules, remember Q of the ice is the amount of heat absorbed by the ice. So that is supposed to be joules or kilojoules. I have joules here. So in order to get the heat from the heat of fusion of ice, I need to get rid of moles. Well, moles is on the bottom, so what are you going to do to get rid of moles? Multiply by moles. So then the formula, so Q of ice, if I write it over, Q of ice is going to be the heat of fusion multiplied by what? Multiplied by the number of moles. Okay? Now, I want to find grams. So I need to substitute this. I need to get grams in here, or mass in grams. So let's go back to our understanding of molar mass. So I'll write mm for molar mass. What is molar mass? How do you calculate molar mass? It's the mass in grams divided by the number of moles. So I have mass in grams divided by the number of moles. It's grams per mole, right? That's what molar mass is. So I can manipulate this formula. I can multiply both sides by n, which is the number of moles. So that cancels out. Now I can get n by itself, right? So I get n times the molar mass is equal to the mass in grams. But I want n by itself, so I'm going to now divide by the molar mass on both sides. And so now molar mass cancels out, and I get the number of moles is equal to the mass in grams divided by molar mass. So now that I know this, I can substitute this in for n. So then this becomes, so then this is going to be equal to, let me erase this now because, so now this is going to be equal to the heat of fusion of ice multiplied by n, but I'm going to substitute this in. So it's going to be multiplied by the mass in grams divided by the molar mass. So this is the mass of the ice, and I'll put ice in there, mass of ice, divided by the molar mass, which is water, the molar mass of water. So now this is my formula for ice. So now I can substitute that in for Q. What about Q of water? This is also important. Well, what is the water? This is the water after all of the ice melted. So the total mass we're given is 20 grams of ice water. It's 20 grams of ice plus liquid water. So 20.0 grams is equal to the mass in grams of ice plus the mass in grams of the water that was there with the ice. It's a mixture. So the mass of the water, this is going to be the water after the ice has melted, right? Because we're taking this in two parts. So the water, the heat that's used to melt the ice Once the ice is melted, it's going to be 20 grams of water. Why? Because the mass of the ice does not change when it goes from solid to liquid. So this 20 grams then becomes all water. So that's going to be the mass of the total water that was there to begin with, right? So the mass of the ice and the water. So what's the best way to think about this? So this is going to melt. The mass of the ice doesn't melt, so both of these together, it's 20 grams, is going to be the mass of the liquid water that is going to absorb more heat. So then this is going to be the mass of the water, which is going to be the ice plus the water. This is going to be the total that was there. That's going to be the 20 grams multiplied by the specific heat of the water multiplied by the temperature change of the water. Again, this is after the melting of the ice. After the melting of the ice. And again, remember that delta T is equal to final temperature minus the initial temperature. This is very important to remember. Don't forget this. Don't flip it. Otherwise, you're going to get a different sign, and that's going to mess up the calculation. So final minus initial, always. Okay, and the block of the iron, that is going to be, same thing, it's going to be the mass of the iron. We're going to use our Q equals MCAT equation, just like we did here. So it's going to be the mass of the iron multiplied by the specific heat of the iron multiplied by the temperature change of the iron. And again, temperature changes final minus initial. So now that we have our formulas, we can plug the formulas into our equation here. So here we're going to have 0 is equal to the Q of the ice. And our Q of the ice is this one here. So it's going to be the heat of fusion of ice multiplied by the mass of the ice that we're looking for divided by the molar mass of water plus, now it's going to be Q of the water. So it's going to be this formula. I'm going to subtract this for Q of the water. So it's going to be the mass of the water once the ice is melted times the specific heat of water times the change in water, which is going to be final minus the initial plus the Q of the iron, which is going to be this formula here. So it's going to be mass of the iron multiplied by the specific heat of the iron multiplied by the temperature change of the iron. Here, let me put this down here so I have room, plus the mass of the iron times the specific heat of the iron times the temperature change final minus initial of the iron. So there's my formula. This is my formula here. So now all I need to do is plug everything in and simplify. So I'm going to go ahead and erase all of this since I don't need this and I need more space. Okay, so 0 is going to be equal to this. What's the heat of fusion? That's given right here. The heat of fusion, 6.02, so 6.02, and that's going to be, I'm sorry, 6,020 because I changed it to joules. So it's going to be 6,020 joules multiplied, and this is joules per mole. So joules per mole multiplied by the mass of the ice, which I don't know, divided by the molar mass of water, which is 18.016 grams per mole. Because that's molar mass. You got to remember that molar mass has units grams per mole. Okay, so that's the first part. The second part here is going to be the mass of the water. Now that's the mass of the water after the ice is melted, so it's going to be 20 grams because the mass of the ice after melting is still the same, so both of these are still going to equal to 20 even after the ice is melted. So this is going to be 20.0 grams multiplied by the specific heat of water, which is 4.18. So 4.18 joules per gram degrees Celsius, multiplied by the temperature change, final minus initial. So the final temperature we're told is 2.0 degrees Celsius. So it's going to be 2.0 degrees Celsius minus the initial temperature, which we are told for the water was 0.0 degrees Celsius. So it's 0.0 degrees Celsius. And then we're going to add this part here. So let me erase this so I can give myself some room. So we're going to add the mass of the iron. So the mass of the iron was 12.5 grams. So that's going to be 12.5 grams multiplied by the specific heat of the iron, which is 0.449. 0.449 joules per gram degrees Celsius. And then, of course, multiplied by the temperature change, which in this case is going to be final temperature again is 2.0 degrees Celsius. And again, let me bring this down here. So it's going to be 12.5 grams multiplied by 0.449 joules per gram degrees Celsius, multiplied by the temperature change, final minus initial. Final is 2.0 degrees Celsius. Final, the initial was 195.0, so 195.0 degrees Celsius. And so here's my equation. So now all I need to do is simplify, multiply, and divide. So here, notice I have joules over mole. I'm going to divide by grams over mole. That means the moles here are going to cancel out. And when I divide these two, I get what do I get? Oops. Sorry about that. I get 334.15. So this is going to be 0 is equal to 334.15, and it's going to end up being joules over gram multiplied by the mass of the ice. Mass of the ice. Okay, so here I have 3 sig figs. So remember, this is when I multiply by 1,000, the last digit was 2. So that's my last significant figure. So I have 3 here, 5 here. So that's going to end here. So I should have 3 sig figs in my answer here. Because remember, the rule is when you multiply and divide, the answer should have the same number of sig figs as the least number. So this has 3, this has 5. Okay, now I need to simplify this. So here, grams are going to cancel out. Degrees Celsius are going to cancel out. So I'm left with joules here. So it's going to be plus, and when I multiply 20 times this, this is going to be 2, right? So when I multiply all of that together, I get what do I get? I'm going to get 167.2. 167.2 joules of energy. So I got that taken care of. And now all I need to do is do the same thing here. So 12.5, again, grams are going to cancel out. The degrees Celsius are going to cancel out. So again, this is going to be a negative, right? So I got a negative change here. So 2 minus 195 is going to be 193 negative. And then I'm going to multiply that. So I should get a negative value here. And when I do that, I get negative 1083.21. So negative 1083.21 joules. Excellent. So now that I have joules here and joules here, I'm going to add these together to get the full amount here. And when I add those together, I get negative 916.01. So that's going to be 0 is equal to 334.15 joules per gram. Again, this sig fig is here. Last sig fig, so 3 sig figs. Again, multiplied by the mass of the ice. And then this is going to be negative, what did I say? 916.01. 916.01 joules. And then I'm going to bring this over to this side because I want to get the mass of the ice by itself. So I'm going to bring joules over here. So I'm going to add 916.01 joules to both sides plus 916.01 joules. So I end up getting a positive 916.01 joules equal to this here, which is going to be 334.15 joules per gram multiplied by the mass of the ice. So now let me bring this up here. So let me get rid of this. I don't need this anymore. Give myself some space. So I'm going to take this and write it up here. So I have 916.01 joules is equal to 334.15 joules per gram multiplied by the mass of the ice. And again, underline the 4 because here I have 3 sig figs. And then here, all I need to do now is divide both sides by 334.15 joules per gram. Divide this side by 334.15 joules per gram. This is going to cancel out, leaving me with the mass of the ice. And then when I divide this, joules is going to cancel out, leaving me with grams, which is a mass unit. So that matches what I'm looking for. And so when I do the division, the mass of the ice ends up being 2.7 grams. So that is the mass of the ice that was originally in my ice water before I put the block of iron into the water. I hope this was helpful. I hope you enjoyed this video. If this helped you figure out or understand how to attack these calorimetry problems, then by all means, like the video, share the video, hit that notification bell somewhere like around here, the like button, I mean. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, put it down below. If you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.